Hello, welcome to my chemistry video. As you're about to see, this video is a lot, and I wasn't able to cover everything as I decided to focus on like what I thought the most important parts would be. So yeah, also I'd like to thank my friends for helping me out in a part of this, so thank you. And I hope you enjoy watching this video summarizing everything we've learned so far in this semester of chemistry. Hello, welcome to my cooking show. Today, I will be making chocolate chip cookies. Now, you might be wondering, isn't this a video for a chem project? You are correct, it is. I did not forget what I'm supposed to be doing. Okay, so for this chem project, I thought it would be a great idea to show what in the world a synthesis reaction looks like in real life. Though it's not completely the same because, you know, baking products are made out of multiple different elements on the periodic table. This is what I thought of. So, today I will be making chocolate chip cookies using all of these ingredients right here to show on how a synthesis reaction is related and is really similar to baking. So let's get started. So first of all, of course, I'm going to be combining all of these ingredients in front of me. We have oil, we have baking soda, we have brown sugar, just regular sugar, 2 different types of chocolate chips, eggs, vanilla, salt, butter, flour, and we're gonna make cookies. So now, while I'm making these cookies, let me just explain what a synthesis reaction is. So a synthesis reaction is when you have multiple different reactants, like multiple different ingredients when baking, and then you only have one product. Now, for regular synthesis reactions in like chemistry, of course, they're like multiple different like reactants, multiple different like chemicals, and for this, they're like multiple chemicals, like baking soda, for example. But it's still the same concept. You have multiple different reactants or ingredients, and you make one product. So also, you can think of it as before you start the reaction, you have like all of the reactants are separate. But as you're doing the reaction, they all combine together. And then, as you progress, and as you will see shortly, the reaction finishes, or when the reaction is done, all of the products will combine. So I will be back to show what the actual, what it looks like when it's done. Okay, so my cookies have finished baking, and as you can see here, these are now one product. They're just like solid, they're all together. The cookies are now complete. Oh, they're now complete, and they're together like the product. Because, you know, on how earlier there were a bunch of different reactants, like the sugar, the eggs, the flour, and now they're in one piece. They are just the cookies. So yeah, that is my example of a synthesis reaction. Hello, I am here to demonstrate what a double replacement reaction looks like. So we have some volunteers who act as our elements. Over here, before the reaction begins, we have hydrogen and chlorine. Then over here, we have we have sodium and sulfur. So, this is before the reaction happens. As the reaction starts, they switch. So now, our hydrogen is reacting with sulfur and our sodium is reacting with chlorine. And that is what a double replacement reaction looks like. Oh, My teacher posted a new video for those confused on how to find the moles to mass. It'll be nice to get another explanation about it. Okay, I'm recording. Great. Okay. Hello, class. Welcome. I know that I posted the notes recently for chapter 10 and how to find moles, what they are, how to convert them to the mass, and that's actually what I'm going to go over today because I've received a few messages that a few of you have been struggling with how to turn the moles to mass. So I'm just going to do this example problem very quickly. So we have this example problem where we have 0.0450 moles of chromium, and we have to calculate the number of grams that is. So what we're going to do is start out by doing 0.0450 CR. And then what we're going to do is we're going to, I'm going to just put a little multiplication sign. And on the top here, we have the atomic mass of chromium, which you do have in your periodic table, which is 2.00 grams of chromium. Then we're going to, of course, put the line for the division. So now we're going to put that over 1 mole. So now that we have this, we can now cancel our like variables. So we can cancel the like things, which is the moles of CR. Then we can solve it, which we're gonna, you multiply 0.0450 times 52.00. You end up with 2.34 grams, because you have the grams from the CR right here. Grams of CR. And remember that because this, when doing this, you are multiplying to do the lowest number of sig figs. Which in this case is 3. So your answer for this problem would be 2.34 grams of CR. I hope that this helps, and yeah, hope that you can solve the rest of these problems. I will see you at our next Zoom meeting. Bye. Hello. Okay, so I'm going to do an IRL real-life example of limiting reactants and limiting and equations. So let's say I'm assembling gift bags. So I have with me here 5 bags, right? And I want to put in pom-poms and bows. Don't ask why. That's just like what we're doing. Maybe we'll make something with them. So in each bag we are going to put in, let's say, 4 bows. So I currently have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I have 18 bows. 18 bows. I have 5 bags, And I also want to put in some mini pom-poms. So we're going to put in 3 per bag. And I have 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I have 20 pom-poms. 20 pom-poms, I have 18 bows, and I have 5 bags. And in each bag, we're going to be putting in 4 bows and 3 pom-poms. Out of all of everything, what would our limiting reactant be? It would be the bows, right? Because if we're putting 4 bows in each bag, then and we have 18 bows, then we would only have enough to make 4 bags. And we have 5 bags total. And then we're putting in 3 pom-poms into each bag. And if we didn't have the limiting of the bows, then we would be able to use up 18 pom-poms out of the 20 that we have. So our limiting reactant here would be the bows. However, let's say that we only had, 3 bags. 3 bags, still the same amount, still 4 bows, and still 3 pom-poms per one. Now what would our limiting reactant be? The bags. We would run out of them. Let's say, I don't actually have more than 5 bags. Let's say, hypothetically speaking, I had, let's say 10 bags with me, and I had 40 bows. Now, our limiting reactant would be the pom-poms, as we only have 20, and we would need 30. So yeah, that's limiting reactants, and that's my example. I don't know why people would want to have bags filled with just bows and pom-poms, but yeah, gift bags. That's an example of a limiting reactant. Oh. Hello. Okay, so in front of me I have a bunch of, or 2 different ingredients. I have washing soda, also known as sodium carbonate, which is NaCO3, and then we also have Epsom salt, which is magnesium sulfate, which is MgSO4. So what are we going to do with these? Well, I'm going to make a precipitate. So when you mix these 2 together, or not mix them just yet, but what I'm gonna do is I'm gonna pour out, I'm going to dissolve both of them in water in 50 mg of water. So let me just pour out 50 milligrams of each. Okay, so 50 milligrams for here, and also pour out milligrams over here. Okay. Now what I'm going to do is I'm going to add 1 teaspoon of each into here, and then I'm going to take it out. And then I'm going to just let both of them dissolve. And while I am letting both of them dissolve, I will explain basically on what is happening, like why the precipitate is forming. So yeah. Also, I will completely say is that I'm trying to be very careful to not get anything on my hands, and be very safe. I do also have gloves here, which I might later, a little bit later. I'm actually combining the 2, and I'm going to be combining them in this clear jar so we can see the precipitate form. So yeah, I'm just going to mix both of them up, and I will come back when the precipitate has formed. But as of right now, I'm just going to be sharing as to what in the world is happening. Okay, hello, welcome. As past me is mixing and making sure that both the Epsom salt and the washing soda solutions are completely dissolved, I current me is going to be explaining on what is happening. Why am I doing this experiment, and what can you expect, and why does it happen? So, when we start out the experiment, we have the washing soda, which is also referred to as sodium carbonate, which is Na2CO3, and we have the Epsom salt, which is magnesium sulfate, and its formula is MgSO4. So, as we start out the equation, both of the solutions will completely dissolve in water. We have the Na2CO3 completely dissolved, it's completely soluble, and we have the MgSO4, which is also completely soluble and will dissolve in water. However, when you combine the two, as you will see shortly, we have the Na2SO4, the Na from the washing soda, and the SO4 from the Epsom salt. It will still completely dissolve. It will still be completely soluble. However, when we combine the CO3, the carbonate, and the Mg, the magnesium, together, it will create a precipitate, and that will not dissolve, as you will see shortly. So, when the CO3 combines with the Na, it's soluble in water. However, when the CO3 combines with the Mg, it creates a precipitate, which is what you will be seeing shortly, and that is the explanation as to what happened and why. So, yeah, you will be seeing that clip shortly. Hello, welcome back. Okay, so both of these solutions, both the sodium carbonate and also the magnesium sulfate, both of them have fully dissolved. The water is completely clear. So now what I'm going to do is first I'm going to take the sodium carbonate and pour it into this clear container. This is just like an empty jar. And as you can see, it's completely clear. Nothing is in here. Now, what I'm going to do is pour in the magnesium sulfate. And let's see, precipitate. As you can see, it immediately like fogged. So, yeah, and if you look inside, let's see. If I take one of these stir sticks, like yeah, it completely changed its color. Well, I think that's the precipitate. Fun! And that's how, or this is an actual real life example of finding a precipitate. Oh. Hello, I'm going to be demonstrating the three main phases in states of matters and phase changes. So in front of me I have an ice cube, and we are going to put the ice cube on a small stove, and as of right now, as you can currently see, the ice cube is melting, which is the first phase change. And this is the phase change from going from solid to liquid, and this is occurring because the bonds in the solid are breaking, so they are now becoming a liquid. And I don't know if you can see, but they break very quickly because the bonds in ice actually aren't that strong at all. However, when going from the next stage after this, going from liquid to gas, because I am boiling water via a small amount of water, the bonds in water are actually very strong because they have hydrogen bonds. And hydrogen bonds are some of the strongest bonds, and it means that it takes a lot of energy to boil and to break the bonds. Unlike another substance, like say iron. I don't have iron. I can't show you iron nor compare it to iron, but yeah. So as you can see now, the water is currently boiling, which is the next phase change. This happens from liquid, this is like the starting point from liquid to gas. and soon it will start to boil, or not boil, start to vaporize. It hasn't started yet because, as I said earlier, hydrogen bonds are very, very strong, so like they take a lot to boil. Oh, but I don't know if you can see that, but there is a tiny bit, I think, of steam coming off of this, which means it is starting to vaporize, and that is changing from liquid to gas. But as of right now, the water is just mostly boiling, but it will start vaporizing. But that is the three, like some of the phase changes and the states of matter. There's also more. There's also ones changing directly from gas to solid and solid to gas. However, that would require me to have like dry ice, which I do not have access to. Otherwise, I would have done an experiment involving dry ice, but I don't have that. So I'm boiling an ice cube until, oops, I don't know if you can tell, there is like a tiny bit of vaporization. But yeah, that's phase changes. Hello, I'm going to show you on how temperature and volume are related from our chapter. So what I'm gonna do is I'm gonna blow up this balloon and then put it in this beaker and then put boiling water. As you can see, it's currently right behind me. So then we can like see. Okay, that's good. Okay, so what I'm gonna do is I'm going to tie the balloon closed. And just tie the balloon on. Okay, so we have the balloon in here. Now, what I'm going to do, I'm just gonna very quickly heat up the water again, so then it is like boiling, and it's good. Also boiling. Chemistry. Okay. I now have a small amount of boiling water. So what I'm going to do is pour this in here. Oh, I don't know if you can see this, but as soon as I poured, oh, hot. Okay, that is very hot. Now what I'm gonna do is I'm going to very quickly get this and then put this on top, and I'm just gonna hold this down for about a minute, and then I'll come back. And I think you might actually already be able to see that the balloon has definitely already gotten a lot bigger, and the volume of the balloon increased. So yeah, I'll come back in about like maybe a minute, maybe not a minute, maybe like 10-20 seconds. So yeah. Okay, so the balloon has been sitting in the water. So what I'm gonna do now is take it out and hold it in my hands. And the balloon is still warm. And I don't know if you can tell on camera, but the balloon is getting, or is like bigger than it was before. Before I had put it into the water, like the water is still like warm. So yeah, it happened really quickly, and like deflated again very quickly. But yeah, that's the experiment. The balloon, oh, and also the balloon the balloon expanding and then like going back down in size is related to the temperature, because the temperature and the volume of objects are directly proportional, and this is due to Charles' law which states that temperature and volume are proportional. So when one increases, or when temperature increases, the volume increases, or when temperature decreases, the volume decreases. So yeah, that's that. Hello. Okay, so I will be demonstrating what an endothermic reaction basically is like, using the materials in front of me. So in front of me, I have a water bottle filled with cold water, and then I also have a bowl filled with just like room temperature water. So this water bottle will be our system. This is where the heat will go into, and then the water inside of here will be our surroundings. So when I put the water bottle into the water, and then I open the water bottle, the heat will flow from the surroundings. The heat is flowing from the surroundings of the water in the bowl into the water bottle, which in turn is making the water colder. And also, because we uncap the water bottle in here, the bonds, this represents the bonds breaking, which is the cap being opened and the water like going out into the surroundings from the system, which is basically like what an endothermic reaction is kind of like. It's not exactly, like, it's the best way I could visualize and completely. So yeah, I will also be back in a second to show what an exothermic reaction is like. Yeah. Okay, so I'm back with an example of an exothermic reaction. This one is very self-explanatory, very easy. It's like very, yeah. So in front with me, I have a lighter. This lighter will be our system. The energy will be flowing out, creating the fire, and then the surroundings are the surroundings around me, just like the atmosphere and everything. So when I turn on the lighter, we have fire. That is, energy is being pushed out and creating fire. And if I hold my hand like kind of close, it's warm around it. The surroundings are heating up because of the fire that is nearby. And that is a very simple but an example of an exothermic reaction. Yeah.